So, Dr. Pearce again, good afternoon. Question 4 of the 2023 GCSE Chemistry Paper 1 from AQA. In this one, it's asking one of those questions about the bond energy. So which expression shows how to calculate the overall bond energy change for the reaction? Lots of people find these difficult, but what we've got to remember is we have to put energy in, so we put positive energy in to break bonds. So we need to break one hydrogen bond and one chlorine bond. So we can see our number is going to be 436 plus our 346. I can see I am going to make two hydrogen chlorine bonds. Now, when I make bonds, that is the opposite. We have to remove energy. Energy is taken out. It's an exothermic change when that happens. So what we do is take out minus 2 times 432. So let's have a quick look at our expressions. We've got 436 plus 346 minus 2 times 432. So that is our answer there. Okay, so let's have a quick look at the next one. Reaction between hydrogen and chlorine is exothermic. Explain why this reaction releases energy to the surroundings. And that is because more energy is released in forming bonds than is used in breaking bonds. Okay, so figure 4 shows parts of reaction profile for hydrogen and chlorine. So we can see that more energy is released in forming bonds than is used in breaking bonds. And what it's asked us to do is to complete the reaction profile. So it's already told us that this is an exothermic change. So what I'm going to do is I'm going to make sure that where I extend this line, it goes below the level of the reactants. And we're going to put some products in here. What I'm going to do is I'm going to use the reaction above, and I can see that I make 2 HCl. It then asks us to label the activation energy and then to label the overall energy change. So if I look here, this activation energy is the energy difference between the reactants and this top state here, or the transition state, and that is going to be our activation energy. And of course, the activation energy is the amount of energy I have to put in to get the reaction to start. We then have this next one here, and what I'm going to do is I'm going to draw a nice horizontal line that's not particularly horizontal. But what we have here is we have the difference between the energy of the reactants and the energy of the products, and that is going to be the overall energy change. So that's both, or that's all three of those marks. So one mark for making sure it's an exothermic change, one mark for labelling the activation energy, and one mark for labelling the overall energy change. So draw a dot and cross diagram for molecule of hydrogen chloride. Show outer electrons only. So chlorine, I can see, if I look at the periodic table, has 7 outer electrons. So we've got 1, 2, 3, 4, 5, 6, 7. Now, chlorine needs to have a full outer shell, so it can either lose 7 electrons or it can gain 1 electron. So I can see it's going to be easier for it to gain that 1 electron. So hydrogen happens to have 1 electron, and hydrogen is a lot smaller than chlorine. So hydrogen only has that inner shell, so it actually only needs one extra electron to get a full outer shell. So the extra electron is here, so that's our dot. And this one here is our cross. So we can see hydrogen has its 2 outer electrons now, one of which it shares with chlorine, so that's 1 and 2. And then chlorine has its 8 outer electrons, one of which it shares with hydrogen. So that's 1, 2, 3, 4, 5, 6, 7, 8. So figure 5 represents molecules of methane and polyethylene. Methane is a gas at room temperature, but is a solid at, but polyethylene is a solid at room temperature. Explain why methane and polyethylene exist at different states. Now, the first thing to look at with this, methane has 2 non-metals in it, so 2 non-metals, C and H. So that is covalently bonded. And is a simple covalent molecule. So it's a simple covalent molecule. Polyethylene is covalently bonded. But is a polymer. Now, what we have to think about is what are we doing to make methane a gas, and if we wanted to make polyethylene a gas, how would we do that? And what we'd have to be splitting up is the intermolecular forces between the different molecules. So methane, when we're turning it into a gas or when we're turning it into a liquid or a solid, we're either breaking or forming intermolecular forces. So if we put a little bit of energy into methane, it will break the intermolecular forces because they're going to be very, very weak between methane molecules. But because polyethylene is a much longer molecule, it will have more intermolecular forces, which is going to take more energy to break. So how do we write this? What do we do? What we do is we say methane has few weak intermolecular forces, which need little energy to overcome. Polyethylene has many intermolecular forces which take more energy to overcome. Okay, and I think that is the end of question 4. Yes, it is.